それでは早速次の講演へと移らせていただきたいと思います。リバースエンジニアリングの考古学的なアプローチ、複数のバージョン、複数のデバイスをリバースエンジニアリングして複雑なパズルを組み立てると題しまして、シュローミ・オーバーマンさんとモシェ・コルさん、そしてアリエル・ションさんにお話をいただきたいと思います。ご紹介させていただきます。シュローミさんはイスラエルの国防軍インテリジェンヌ部隊のベテランであり、過去にはコードブルーでも講演をしております。そしてリップル 2.0 では今年非常に話題となりましたが、サプライチェーンの数百ものデバイスに影響を与える脆弱性などを苦労なく発見できる手法にも触れていただきます。シュローミさん、モシェさん、アリエルさんからは今回のテーマについての動画をいただいております。それでは早速動画をご覧ください。
This is our second take because unfortunately we were able to do the whole first run without recording. So hello again from us. A little bit about who we are. So we're JSOF, a software security consultancy that does a lot of security research and penetration testing, focusing mostly on IoT. My name is Shlomi Oberman. I'm a co-founder of JSOF. And we'll be speaking with me today Moshe Kol, a security researcher at JSOF, who is also the founder of the Ripple 20 Vulnerabilities, and Ariel Shawn, a security researcher at JSOF, who was involved in the exploitation and reverse engineering process of Ripple 20. What we'll be talking about today is a little bit of background about Ripple 20 for those of you who haven't heard about it, and some pointers on where to find more information. And then we'll go in depth into the reverse engineering process of Ripple 20 and talk about some of the different binaries that we had to reverse engineer in order to piece together a complex puzzle. We'll then do a wrap up with some of the conclusions that can be drawn from what we've seen about what vulnerabilities look like in the supply chain, and what reuse of code looks like in the supply chain. So, Ripple 20. Ripple 20 is a series of 19 zero-day vulnerabilities in a TCP/IP communication stack called TREC TCP/IP. These resulted in 24 unique patches, and 2 of the vulnerabilities were reported anonymously, while the rest were reported by JSOF. So it kind of depends how you count, but they were bundled into 19 unique CVEs. And what is interesting about this series of vulnerabilities is that they were amplified by the supply chain. So despite the fact that they were all found in this one piece of software called TREC TCP/IP, this software was written and is still written by an American company called TREC. The fact that TREC had so many clients and sold software for so many years, and the fact that their clients had more clients and more clients, led to the fact that the vulnerabilities were amplified by the supply chain, reaching hundreds of millions of devices in a whole range of verticals. In total, there are probably billions of devices containing the TREC TCP/IP stack, but our estimation is hundreds of millions of devices are actually vulnerable with active code and vulnerabilities. These are the 19 CVEs of Ripple 20. Out of these, 4 are critical remote code execution vulnerabilities, while the other ones have ranging effects such as information leak, denial of service, or other effects. For some devices, of course, denial of service can be quite bad. For other devices, maybe not so much of an issue. So ranging effect and ranging effects per device. The devices affected are devices made by companies you all know, small companies, large companies. This is a list, this is a sort of a sample of some of the better known, at least Western companies. There's a whole Japanese branch of the TREC stack that is found in a whole bunch of Asian companies. And there's of course many more companies. In total, we reached out to over 100 companies. 30-something companies confirmed that they are indeed, their devices are indeed vulnerable to the Ripple 20 vulnerabilities, while a lot of companies didn't reply at all, and many companies also said that they're not vulnerable. So somewhere between 33 confirmed vendors and a few dozen still pending vendors that haven't replied yet. The research itself took something like 9 months with varying intensities and was conducted from the end of 2019 into the beginning of 2020 with the public disclosure in June of 2020. In total, we reverse engineered 7 different devices before the publication date, before the disclosure. We've reverse engineered additional devices since. Some of the devices we reverse engineered in multiple versions. We'll be discussing 5 of these devices today, just due to time limitations and some of the devices being less interesting. You'll see we encountered some pretty strange architectures, firmwares, and operating systems. The results of this research are quite heavily documented in 2 white papers, as well as our Black Hat and DEF CON talk, and on our website. So anyone looking for more technical details or details about the impact, feel free to go to those resources. Or, of course, feel free to reach out. So the challenge that we faced when we started looking into Ripple 20, except for the fact that we at first didn't even know where to look, which devices use Trek, etc., how to find devices, is the fact that despite being one piece of code, there are many versions. So different vendors will compile the code differently, they'll use different parts of the code, and the code changes over the years. We knew at the start that there'd be several differences between vendors, but little did we know at the start how complex and how different the devices would look like. We also needed as much information as possible, ideally debug symbols, the ability to actually perform debugging, the ability to get firmwares, etc. And we needed to get multiple data points from different years and different vendors in order to piece together the whole history. As we started working on Trek, we assembled the binaries. We assembled the different devices. We found most of them on the internet. Some of them we had to purchase, and they came with a binary, as you'll see. And as we started, as we did the reverse engineering, and we figured that we're looking at things from different years, different vendors, different branches, different compilations, we started calling this an archeology project, because we were digging into the binary in order to understand what happened historically. Of course, this is not actual archaeology, so we're talking about pre-2000 years. This is our prehistory for the Trek TCP/IP stack, and prehistory for many of the devices we use. But we found some pretty old code. I think the oldest code that we saw in a running device was from 2007, give or take. I'll now transfer the mic over to Moshe Kol, who will be talking about some of the binaries we looked at.
Thanks, Shlomi. I'm Moshe Kol. I'm security researcher at JSOF, and I'll begin with how we started the research, and I'll talk about some of the binaries. So we started the research by browsing to Trek website, where we wanted to learn some more information about the Trek TCP/IP stack. So we were looking for data sheets, manual demos, anything that can help us uncover the mystery around this TCP/IP stack. So we found that Trek offers several demos. One of these demos was a Freescale 5208 demo. And from this demo, we were able to extract some useful header files with function names, structure definitions, some comments, and also the binary itself contained some function names and some debug symbols. So to some extent, we were able to learn some information from this demo file. The main disadvantage of this demo file is that we didn't have debug capabilities, so we were looking more closely into the Trek demo for Windows. So this is our first binary. So Trek used to offer Windows 32-bit demo, I say used to because now they dropped this demo from the website, but you can still get it if you want. You can see in this demo, Track offers some useful features, some interesting features that we wanted to look at, such as IPv4, IPv6, a DHCP client, TCP, UDP, ICMP, etc. So this was good from our perspective because we can reverse engineer this binary. This is just a Win32 binary, and we can debug it. We found some vulnerabilities in this stage. For example, some of the vulnerabilities, one of the vulnerabilities we found was tracked by CB20 11.896, which involved an issue with how the track stack handles fragments over an IP and IP tunnel. And we wanted to test if other devices are affected by this serious vulnerability. So at this point we searched online for devices which run track, and we found this device of a company named Digi, and we simply found a message on an online forum that says that Digi Connect uses the track TCP IP stack. So we decided to buy this device, this Digi Connect device. You can see it looks like an Ethernet connector, but it's actually full system on module in this little device. And it comes in two flavors. The first flavor runs embedded Linux, and the second runs a proprietary NetPlus OS. And the network stack of the NetPlus OS is track TCP IP, at least in versions greater than 7.0. So we bought the ConnectME development kit, and the use of the development kit helped us getting started and getting debug capabilities for this device. So we found that this new Digi device runs on ARM9 processor. We have debugging capabilities using JTAG interface, and it comes with an Eclipse-based IDE, so we can write software onto this device. So we compiled a simple software. We extracted the else file, the result again file, and we found that the else file comes with debug symbols. So we have now function names, names of global variables, some structure definitions, and offsets. So this really helped us gaining more information regarding the track TCP IP stack. We also developed an exploit for the previously found vulnerabilities, the vulnerability that we found in the demo. And the disadvantage of using this device is that we found that it uses relatively old track version. So we wanted to find at this point if the vulnerability affects the most recent track version. So we looked for another data point, another binary. So this led us to Intel AMT. We found that track powers the AMT module of Intel ME. And we speculated that since Intel is a security aware company, they must have updated their track software, so they are using the most recent track TCP IP stack with the latest update. So that's what we hoped. And upon looking at the binary, we saw that Intel had some defensive programming, by which I mean that they check various length fields in the packet, something we did not see in the previous two binaries. And these checks render our previous exploit as the vulnerability was fixed basically in these binaries, and we thought we had 1 days that still existed in the wild, and we were mostly wrong, as Track told us. I'll talk about this later. So we thought that these may be fixes, maybe some compile time macro, or maybe Intel are just paranoid. So during the research, Intel published a security advisory, and one of the vulnerabilities in this security advisory catches our interest. So you can see the description on the slide. It says that insufficient input validation vulnerability exists in subsystem in Intel AMT that may allow an unauthenticated user to potentially enable denial of service or information disclosure via adjacent access. So by adjacent access, we suppose they mean something that is local to the network link, such as ARP or DCP. So this looks very promising, and you see the CVSS score of high, and we wanted to patch the AMT versions to find the vulnerability, because we suspected this vulnerability lies in the track code, basically. So we obtained two ME firmware versions online, you can find them, and we wanted to patch diff between these two versions. We used the ME analyzer tool to unpack the firmware and extract the AMT module, and we used bindiff as our patch diffing tool. And what we found a fixed bug in the DCP v6 client of track. So during option 24 in DCP v6, which is the domain search list option, in the function DCP set reply info, which commits the data received from the DCP v6 server. So we found a read out of bound vulnerability. You can see in this snippet of code, they iterate over length bytes of a label, and they don't check bounds on the buffer. So this snippet very much feels like the description of the vulnerability we saw before, because it's DTP v6, so adjacent access, and also this out-of-bound access may cause information leak or denial of service. For example, if we read from an AppMap page. So we thought we found this vulnerability, and we also found that track got the fix wrong. So you can see in this snippet of code, which is from the more newer version of Intel AMT, you can see that they now check the total length value against some constant, but you still have out-of-band access. So the fix was basically not implemented correctly. So we reported the issue to track, and this issue was assigned the CVE 2020-11905. So the story behind Intel AMT is interesting. So some of the vulnerabilities fixed only in Intel. Also, Intel has exploit mitigation. Digi, on the other hand, had old code. Intel had new code. Intel had some code, not all of the code. So until disclosure, we thought that some bugs were 1 days, and Intel was the most updated. But actually, track told us that these are actually 0 day. So the story behind AMT is unclear. Maybe Intel fixed the issues independently. So to summarize, there are a few types of track supply chain vulnerabilities. Ones that are true 0 days, ones that are 0 days that only fix in Intel and AMT code to our knowledge and not in track upstream, and vulnerabilities that are end days that exist in the wild and fixed upstream, but never actually publicly reported as far as we know, and we actually don't know if these are considered security fixes. So it works like this. If you have a support package of track, then you get updates, feature updates, and security updates, and if you have no support, then you get no security. Another device that we looked at is HP printer. So we just googled the common track function names in Google, and we found that HP printers uses track. as their TCP/IP stack, and we wanted to check if they are affected by the vulnerabilities. So the first step was to obtain the firmware, and we were able to obtain the firmware from HP's public FTP server. So we obtained an RFU file, which is a remote firmware update file, which was highly packed and highly compressed format. It requires multi-stage unpacking, and the file formats were relatively bizarre. You can see the whole process is described in our 4-part blog post. And then in HP printers, we found the vulnerability variant. We found that the previously found vulnerability in the track demo, and which was exploited in Digi CB20 11.896, crashes the printer instead of triggering remote code execution. So you can see in the snippet here that the same condition that should actually cause inconsistency and that will lead to remote code execution now causes TF kernel error function to be executed. And when TF kernel error executed, it causes a kernel panic on HP printers. So this causes a printer crash. So this is the vulnerability variant of the remote code execution vulnerability. So you can see how different configurations and maybe if-defs affect the research process and the research outcomes, basically. So now I'll hand over the mic to Ariel Schon. He will talk about a fifth binary of a UPS device from Schneider Electric.
Thank you, Moshe. I'm Ariel. I'm also a security researcher at JSOF, and I'm going to talk about the firmware on the Schneider Electric APC UPS device. So UPS is an uninterruptible power supply, and this device by Schneider has a network card running a firmware called APC OS, which features the track TCP/IP stack. So we initially got the firmware directly from the APC website. When we downloaded it as an executable, which will update the firmware of the device over the network. And from this executable, we extracted the firmware files. And luckily, they were neither encrypted or compressed, so that was relatively straightforward. And we did have to reverse engineer some parts of the firmware image just to understand how to properly load it into our disassembler. But that was relatively easy. And after that, we identified some x86 16-bit opcodes. So we loaded it into Ghidra with the right processor module, but we saw that it only kind of works. The disassembler didn't manage to resolve far calls in the code, and we didn't have many extracts. So we understood that maybe our processor module is not a great fit. And the memory addressing in particular looked very strange. We saw x86 opcodes, but the segments didn't check out. And we figured it can't be protected mode because there were a ton of segments and we couldn't find the GBT in any of the firmware files. And it can't be a real mode either because a simple shift of the segment part of an address by 4 bits didn't lead to any code in the example of the far code. So we tried to learn more about x86 and find some of the weirder operation modes to find something that fits, but we didn't have any luck. Luckily, we noticed a pattern noticed initially in strings that the least significant byte of a string's effective address appears in push instructions in the vicinity of the string. So we figured this is most likely the string is actually pushed as an argument to some string manipulating function. So we figured this is not a coincidence, and as you can see, this pattern is just right for a shift by 8 bits instead of 4 bits. So we manually tried to shift some far calls by 8 bits instead of 4 bits and some pushes of strings, and we saw everything checks out, and far calls actually resolve to function prologue. So this was the solution. Initially we didn't understand exactly why and what does this mean, but it still worked, so we tried to implement it. Initially we tried to recompile Ghidra's x86 processor module to support the 8-bit shift, but that didn't really work. We didn't have any string xrefs, and also some of the far calls were still broken, so that didn't work out. We also tried to do something similar in the configuration of Vadame, which resulted in a better firmware image, but still it lacked strings and other xrefs. And finally, we found a solution on OpenRCE. Some guy that posted this exact problem in 2008, and the great Igor Skoshinsky offered a solution that also worked for us, to simply create a lot of segment selectors in IDA with the 8-bit shift already calculated in. So we did this using an IDA script that iterated over the far calls and generated the right segments, and then we could actually start reverse engineering. So when we reverse engineered, we found on the device a newer version of Trek than the one we found on the Digi device Moshe talked about earlier. And in this version, we also found a new vulnerability of the CB20 11901 family of vulnerabilities, and we call this one the Bad Arduino Vulnerability, which essentially results from a bad fix of a previous vulnerability in the same family. This vulnerability did not exist in Intel AMT simply because they turned off this feature, so the code is not there, it's not used. Now I'll pass the mic back to Shlomi for a wrap-up.
Before I wrap up and draw some conclusions, let me just mention that, of course, most of the vendors that we discussed and most of the devices that we discussed do have patches available, so as long as you are running the latest versions of the devices, they are no longer affected and the vulnerabilities are fixed. This was reported back in June, so there are patches for everything available. What conclusions can we draw and what takeaways can we take from what we've learned from reverse engineering all these binaries and the vulnerabilities that we saw? One thing we can definitely say is that the supply chain is complicated and complex. We looked at these different binaries. Every binary taught us something new. If we look at more binaries now, we still learn new things about the Trek stack. So supply chain can get very complex. Second thing is that obscurity mostly doesn't work. So despite the fact that HP firmwares were compressed in multiple levels, despite the fact that this is a proprietary piece of software, despite the fact that the supply chain was mostly obscure and completely not public, and maybe because of these reasons, still we were able to find lots of vulnerabilities that affect all of these devices. A key takeaway, both for asset owners and for device manufacturers, is that they should know where their code comes from, and they should make sure that the code that comes from third parties is ideally fresh, but even if not fresh, that all vulnerability fixes and patches are taken from the upstream suppliers, and that they know when there are security fixes. This also means keeping an update package, a support package in place in most cases. And very important, the deeper we go in the supply chain, and Trek was pretty deep in the supply chain, the higher the security impact and the wider the security impact. This has implications both for target selection for researchers, but also for device manufacturers and suppliers of code. If your code is going to run in billions of different devices, maybe it's more important to review that code for security issues than other code that will only run on 1 or 2 or 3 devices. One interesting side effect of Ripple 20 and of supply chain issues in general is that patch propagations happen at different paces. So if one vendor patches and another vendor doesn't patch, then a security researcher or a malicious actor can look at the difference between these two vendors, between these two firmwares, and find vulnerabilities for free, right? So if Intel AMT update their firmware and fix it, but a different vendor doesn't apply the fix, especially if the fix wasn't public and they might not even know about the fix, or they missed the fix, they might have a vulnerability that is much easier to find. There's no research that needs to be done. Just look at the difference between the versions, look what was patched in one vendor, and you find vulnerabilities in another vendor. Kind of like patch gapping, but on steroids, because this could be going on for years. So to summarize, we went through a complex reverse engineering process, multiple different binaries, different architectures, different reverse engineering challenges, a lot of forks in the software library. The different forks revealed more vulnerabilities as we did patch diffing and as we found bad fixes, and different vendors using different parts of the code and compiling it differently. Supply chain makes security extremely difficult for everybody involved in the supply chain, and we need new ways to communicate and new ways to deal with these issues. And we learned that the proprietary update process is extremely obscure. Nobody exactly knows exactly how this is supposed to work, and nobody knows exactly how this does work. Oftentimes it works differently for every vendor and for every case. Thank you very much for listening to our talk. Feel free to reach out to us. Feel free to reach out to us on our email, follow us on our Twitter and our LinkedIn, and feel free to look at the other information released about Ripple 20 in different media.